loud. All right, so now we go and take this and we wonder, how do I do a single instruction with multiple data? On this guy, it's just like a MATLAB command. X bar equals X bar plus 1. So what does that do? It adds 1 to each of the elements in X. This X vector can now be operated on with one operation on all the data. That is what you call a vector machine. That's really useful for multimedia programming. And in fact, when we look at Intel's marketing, we see the MMX are multimedia instruction sets coming into the Pentium-style processors fairly early on. Not to be outdone, IBM had its PowerPC line coming in with something called AltiVec. Well, probably about 2004, actually. AltiVec was the first. MMX was Intel's approach to try and combat AltiVec. And so what they did was they incorporated these instructions directly into the CPU. You say you're going to double the number of transistors. What are we going to do with all those transistors? This is the kind of thing we do. We put in a vector processing unit, or VPU. VPU. You put the vector processing unit into the CPU, and now you have the ability to take several pieces of data and operate on them all at the same time, turning your CPU into a SIMD-compliant architecture. Now, some companies really emphasize SIMD because they know they're dealing with a pipeline of numbers that are going to be streaming in indefinitely. And NVIDIA is making these so-called Tesla cards with CUDA processors that are essentially SIMD machines. And so as a result, they're very specialized and extraordinarily fast because they're really good at doing vector operations. If you can specialize a machine to do one thing really well, you can make it really fast. So if all you want to do with your chip is mine Bitcoin, and you're going to build Bitcoin mining chips, you can make them really good at mining Bitcoin. SIMD. So now we've got SISD, scalar and superscalar, and we have SIMD. This is vector. Other vector architectures include DSP chips, because the DSP chip is meant to process a stream of data coming in. If I'm a manufacturer of televisions or streaming decode devices like Amazon Fire Sticks or Roku or Apple TVs, I really want to have vector coprocessors in the form of DSP chips or DSP cores that I can drop in to my CPU die so that I can proceed to exploit my extra transistors from Moore's Law and get good throughput for decoding streaming data and for encoding it, for that matter. And so it is the case that we really do want these vector coprocessors to be available to us when we design our computers. (1966), huh? Michael Flynn used SISD, SIMD, MISD, and MIMD. And this gave us a question in homework number 3, problem 6, and the answer is true. these are the various broad architectures that we have to deal with. Let's take a minute and talk a little bit about multiple instructions with single data. Why would you want to have multiple instructions operate on single data? If you had multiple CPUs operating on the same data, they could work in parallel and check each other. So this might be really good for the avionics of something that's mission critical. So this is what you might call redundancy. And with redundancy, we can obtain reliability. In other words, if I had multiple cores all doing exactly the same thing on exactly the same data, I could have the cores check each other and make sure there aren't any errors. Why should there be errors? Well, if it's a aerospace application where you're deploying into deep space, you might have cosmic radiation messing up the flip-flops. In the space station, they have CCD cameras with bad pixels. Little holes in the image. You can barely see them, but if you zoom in, you can see the bad pixels. And this comes about because the cosmic rays hit the CCDs and they destroy individual transistors. Cosmic rays go through everything. This is one of the basic fundamental limitations to travel to Mars. Right? Astronauts cannot have enough shielding to prevent cosmic rays from penetrating their bodies. Radiation comes in two forms: ionizing radiation and non-ionizing radiation. Non-ionizing radiation is like the warmth that you get from infrared rays that come from the sun. It feels good, makes you nice and warm, and it's great. Ionizing radiation is like the ultraviolet light. The ultraviolet light in the sun is able to knock an electron out of the orbit in an atom. When that happens, that ionizes the atom, and it causes mutation. And when there's mutation, the body can repair it, right? But only to a certain extent. After a fashion, the mutation cannot be repaired. And when that occurs, that's when you get the cancers. So ionizing radiation, it's not the 2 gigahertz radiation from Wi-Fi. It's more like the 13 nanometer stuff that comes out of the EUV machine over at the Twin Skin. It's a soft X-ray. Anything that frequency or higher is basically dangerous to humans. And then comes MIMD. Multiple instructions, multiple data, and this is true concurrency. And we can see this happening when you have multiple cores. And that's become, as we saw in our last lecture, almost taken for granted. Didn't used to be, almost taken for granted. You can also find it in NOW's network of workstations. So I can have a whole pile of computers sitting around, I don't know, quietly depreciating, sucking down power, throwing off heat, and doing nothing all summer long, all night long, all weekend long, sitting around here on campus. But if you put in a CPU harvesting screensaver, they can volunteer or scavenge their CPU cycles for useful tasks. So this is actually a very green way to deal with a network of workstations. And they don't need fine-grained parallelism if you can find tasks that can be divided up so that they don't overwhelm a server with overhead and communication. So for example, if you're Disney and you want to make a movie, it might take you 10, 20 minutes to do a high-resolution frame. You could have each frame done on a separate computer. They're all sitting on a network, and they can join each other after they're done. And you can have one server that sort of assembles the movie while the other ones all do the rendering. That's MIMD. So that's kind of interesting, right? Multiple data. If you think about it, every time you move the camera, you've got a slightly different view of the scene that's changed the data, and you can effectively have very similar kind of rendering being done on each one of the frames. So the geometry is changing. So that kind of summarizes the architecture. We got the Flynn taxonomy, superscalar. We talked a little bit about CISC versus RISC. And we talked about the core wars last time. So that got us pretty far. I think that's pretty good. What do you think? Any questions? So let's do an example. This is coming from question 14. Homework number 3. It's like a arithmetic logic unit. ALUs typically can do add, subtract, multiply, and divide. There may be other things they can do, but that's about it. I mean, you could invert, you could have an ALU do a whole bunch of different interesting and wonderful things. Well, now let's see. So there's the ALU. It'll have an A input and a B input. And what we'll do is we'll have some sort of memory. And the memory, well, let's not get too fine-grained with this. But the memory can feed a register we'll call the accumulator. And it can also feed the ALU. The accumulator can feed the input to the ALU. And somewhere in here, there's a finite state machine that controls the sequence of instruction fetch, instruction decode. And each instruction is called an operational code, or opcode. And the opcode goes into a thing called the instruction register. This basic architecture is going to feed the finite state machine, which will determine what it does with the accumulator, the ALU, and somewhere in here we'd like to have a memory address register, also known as the program counter. I'm going to use program counter, that's okay. They're interchangeable. So here's the program counter, and that shows us where we are in memory. That gives us an address. And what we'll do is we'll use our instruction register to modify the program counter so we can have jumps or we can have simple increments. And that's about all I want to do, other than find a way to take the output of the ALU and perhaps run it into our accumulator. So we'll just run that into the accumulator as well if we want to store something. So that's sort of my block diagram. What kind of architecture is this? Making reference now to the Flynn taxonomy. Right? I know what an ALU is. I know what memory is. Program counter is just a counter. Instruction register, that's D flip-flops. Finite state machines, I know what they are. Accumulator, that's just another register. And that's my CPU. That's the block diagram. This is out of question 14, homework number 3. What's this architecture using Flynn taxonomy? Is it a superscalar architecture? Well, let's look at the choices. It's SIMD, SISD, MIMD, or MISD. Which one is it? I'm probably going to start calling on people. Let's see. Is John Baker here? Is Shamrock here? Shamrock Barrow? Yes. What do you think the architecture is, Shamrock? MISD, multiple instructions, single data. Where would we get multiple instructions from? Yeah, I mean, the finite state machine is processing one instruction from the instruction register at a time. What else could it be? Is Alexander here? Stephanie is here. Stephanie, what could it be? I'm going to silence my phone. Sorry about that. Say it again. SISD. Yes, that's correct. Single instruction, single data. Right? This is the kind of CPU you might start with if you were designing a CPU. I think designing a CPU sounds like an excellent idea for this class. Wouldn't that be fun? So the CPU has to be able to decode instructions from the instruction register that'll cause the finite state machine to do something with all of these resources available to it. The program counter may have to be jam loaded with another address if the finite state machine sees an instruction that says something like jump to address 0200. Jump is like a go-to. And what is he doing? He's saying to the program counter, I want you to go to address 0200 for your next instruction because we just did a branch. Somebody said, you know, go to the beginning of the for loop or go to you know, the subroutine down at this address. And then once the program counter gets jam loaded with that, it'll fetch from memory the next instruction, and that'll end up in the instruction register and then proceed to be used to decode something else. Typical assembler. Another one could be branch, comparing the accumulator, branch if not equal to 0. And you might want to branch to 0200, right? It's doing a comparison. I thought I turned this off. Didn't I turn this on? There it goes. Another one might be jump to subroutine at 0200. So what will happen here is it'll execute a bunch of instructions, and at the end it's going to say return the subroutine, RTS. These are all basic assembler mnemonics. And what will happen when you jump to a subroutine is it'll take the current address and push it onto a stack. And return to subroutine is going to pop it off the stack and go back to the other address. It's not a programming language we normally teach here. But this is a very typical sort of thing you might expect the Java compiler to compile into. So if you're talking about what's in those class files that the JavaC creates, when it inputs Java code and outputs a .class file, the answer is bytecodes. And those bytecodes represent a RISC machine. And that RISC machine is going to have each one of these bytecodes with an assembler mnemonic, which you can get, right, using Java. What's going on? Java. J-A-V-A-C, the Java compiler. In fact, you can take these assembly instructions and output class files directly using the Java assembler, known as, well, I can't write over there because I can't see it. Java P. That's the Java assembly, which is also a part of the JDK, or Java Development Kit. And in fact, every CPU, the one in the mobile device that I'm using for recording, the one in the desktop computer, one in all the computers you have an underlying machine code, the so-called exe files. They have these assemblers instructions, and they've been encoded into a binary that's efficient for them to execute by loading from memory using the program counter and this sort of architecture. That's the answer to question number 14. It's SysD. So this is a SysD architecture. And I'll just write that here. Single instruction, single data. This is the simplest of architectures. Yeah. No, I don't think it's available just yet. I beg your pardon? Question 14 in homework 3, yeah. In the homework 3, which I haven't posted yet, but which I will post. I guess it, you know what? I think it's out there. It just hasn't been made available to you. So in principle, I could make it available now so you could see it. Maybe that's the way to go. Let me see if I can get into my Blackboard here. All right, I went to blackboard.fairfield.edu and he says he can't find it. Oh, here it is. And I'll get it up there quickly. Don't worry. So we'll go to courses, and then we'll do computer architecture, and then we'll do course content, and then we'll do homeworks. And we'll go to homework 3, and then we're going to say it's available after September 14th. What's today? The 14th. Oh, it's available at the end of today. I screwed up the availability thing. I should have made it available earlier. Let's try and change that. I'll make the availability Sunday, which is yesterday. Hit submit. See if it's available now. You may have to refresh. Is it available? Yes? Yeah. Cool. Cool. That's cool. All right, so we got a little time. Let's try. So are we good with this? I'm going to erase this now to make some space. What you should do, convert it off. All right. What's this symbol represent? Any ideas? Ever see anything quite like it? What is it? A diode. No, diodes look like this. That's a diode. Any ideas? This is called a tri-state buffer. The tri-state buffer can have its input asserted as 1, and yet its output can be left in a high impedance state if it's turned off. This is a very valuable thing, because if you have a bus, you have to choose what is able to drive that bus. If you have, very simple example, if you have an AND gate, and its output is hooked to another AND gate directly, something bad will happen. Something bad will happen. Suppose you input 0 and 1, and then 1 and 1. What's the output here? Well, let's think about this. The output of the AND gate, when the input is 1 and 1, the output should be 1. The output of the AND gate, when the input is 0 and 1, should be 0. It's there. 1 has a voltage equivalent of 5 volts. 0 has a voltage equivalent of ground. What happens when you take ground and you hook it to 5 volts? Ohm's law. E equals IR. I equals E over R. If you're hooking ground to 5 volts, R goes to 0. What happens to your current? Your current goes to infinity. What happens when you have infinite current? Things get really hot and upset, and nobody likes you, and the world is gloomy, and you get all depressed. These things aren't gates, they're transistors, which are set up to act like gates. What happens if you tell a transistor to sink infinite current? It blows out in nanoseconds. And your gates are broken, and your CPU is broken, and everything is busted. Now, that's not necessarily a bad thing, because if you're not breaking stuff, you're not learning. But if you want your computers to work properly, you don't do this. What you do, if you have to drive a circuit from one of 2 sources, is you insert this guy right in here. And then you do the same thing over here. Now you can wire OR them together. And you're very clever, because what you did was you put an inverter in here. Oops. Let's see if I can do this. Right. And the inverter, there's that. So now you can choose device 1 or 0. And that allows you to choose who's going to drive the output line, either this guy or that guy. When this guy is on, this guy will be in a high impedance state. And when this guy is on, this one will be in a high impedance state. And that high impedance state means the output will not reach the other side, and therefore this will be the dominant AND gate. You need these things, because otherwise you can't have what's called a bus. The bus consists of, I don't know, make up a number, 64 wires, 32 wires, whatever, and it's being driven by multiple cards that are plugged into the bus. all being driven by multiple cards. And you have to choose which card has control over the bus. If they all start asserting the bus at the same time, you're going to have a problem because one of them is going to say, hey, that bus should be ground. And another one's going to say, nope, nope, it's 5 volts. And it's going to go zip, and you're going to have a short, and you're going to blow out boards, like Tesla cards, big expensive boards. And so what you need is you need tri-state buffers, which are going to drive the bus. Now, in the case of the chips, which you can find in our stock room, you can find a 74254. I think that's the number. Let me just check it. Nope, I got it backwards. 245. And this comes in variants. You can have 74LS245. You can have 74HC. 245LS is low power Schottky. HC is high speed CMOS. You can find a whole bunch of these guys, and they are 8-bit octal bus transceivers. In other words, there's 8 of these things, and they have them going in both directions, and they're all in one chip. And so what that means to you, the designer, is you can borrow these things and drop them into your Quartus design document and proceed to use them to create buses that allow you to address stuff like memory, or RAM, or ROM, or maybe other things that you might like to have. So the octal bus transceiver is a useful device in order for you to be able to design systems. It's octal, so it only has 8 bits. And this is the answer to question 15. If you want to use it to isolate a 1024-bit static RAM, it won't work because it's an octal bus transceiver. You need actual 10 bits. So you need a little bit more than an octal transceiver. Maybe 2 octal transceivers would be sufficient. So that's a tri-state buffer. I'm pretty sure we discussed it. It was certainly in the Katz book. And you can look it up in the Katz book if you want. As a practical matter, when you find these things for your little breadboards, when you want to build stuff, real hardware, you'll see there's a little notch that gives you an orientation. That makes this pin 1. Moreover, and you've got to use the data sheet, you'll find that the ground and the VCC are at different locations. So this would be like pin 20. And this might be, I forget how many pins it is, 10, yes? And that would be your ground, and that would be your VCC. And then stuff like this could be the data direction. And then you'd have pins for data going in and pins for data going out. When you take something like this as a DIP, this is a dual inline package, you will find that the spacing for the leads for your breadboard fit exactly because the standard is 0.1 inch. That's the standard. And they use it, same standard, for the mezzanine bus on the Arduino. So when you take Arduino shields, you can plug them straight into your breadboards because they're all using the 0.1 inch standard. Now this is not true for surface mount devices, SMD, surface mount devices. Because surface mount devices are meant to not have pins that go through boards, it allows you to avoid having to drill holes. If you've ever made a printed circuit board and you sat there with a drill press, as I have done, and tiny little drill bits that break all the time, and you start drilling holes through the fiberglass and epoxy printed circuit board substrates, it's not pleasant. And turns out it's terribly time consuming. So going to a surface mount device, you'll find the pinouts are identical, but the device is way, way smaller. And it's quite typical to see sort of a small outline integrated circuit where all of the pins that are coming out, and they're very tiny, have a little, I'll call it kind of a J shape to them. And what you do is you put a little solder paste down, plunk down the chip, and then run it through a reflow oven. And we actually have a reflow machine in the shop upstairs so that you can do a little pick and place operation and do your own surface mount devices. So that's what I have time for today. I think we're almost out of time. Any questions? The Octobus transceiver question came in question 15. So without any further ado, then, I think that's it for today. Stay safe. Thanks a bunch.
Thank you.
Thank
Thank
you.
you.
Yeah.